So in the previous video we solved problems with non-homogeneous Dirichlet boundary conditions, and we introduced what a boundary function is. So in this video we are going to tackle the Neumann boundary conditions. Okay, so first we'll start with homogeneous and then we'll look at non-homogeneous ones. Okay, so let's start with a very simple example which is a second order ODE with two boundary conditions. One is Dirichlet, another is Neumann, and both are homogeneous. Okay, so the first thing that we need to think of is that we have information about a bit of information about our solution, which is the boundary conditions that need to be satisfied. Okay, so I'll start using a term called permissible trial solutions. Okay, so we need to construct such trial solutions which satisfy our boundary conditions. We'll call those trial solutions as the permissible ones. Okay, now how can we construct a trial solution or approximate solution UH such that these two boundary conditions, which is this is the essential and the Neumann boundary conditions, are satisfied? Okay, so let us select our basis function something like this. Okay, this is sinusoidal or the Fourier basis with some which the argument looks a bit messy. So I've constructed this keeping something in mind. So let's see what the first derivative looks like. The first derivative looks something like this. So what's special about these, selecting these as the basis function? The important thing is this: the basis functions, all of the basis functions, psi I, psi 1, psi 2, psi 3, all of the basis functions are 0 at 0, and the first derivative of the basis functions of all the basis functions is at L is 0. Okay, so this is the location at which we have specified the essential and the Neumann boundary conditions, or the Dirichlet and the Neumann boundary conditions. Okay, so we have seen that the part of the boundary at which the essential boundary conditions has been satisfied, essential or the Dirichlet boundary condition has been satisfied, the value of the basis function, all the basis functions should be 0 at that location. Okay, or that part of the boundary. Similarly, if you want to satisfy Neumann boundary condition, then the second derivative of a basis function should be 0 at those part of the boundary at which the Neumann boundary condition has been specified. Okay, so let us calculate the second derivative, and our trial solution now looks something like this. Note that this Ij are this UH is now a permissible trial solution. Why is it so? This is because it will satisfy both of them. Okay, because if you calculate UH dash, it will be Cj times Ij dash, and for all Cij's would be 0 at UH dash at x equals to L, so UH dash at L will be 0. Okay, so far so good. Now we calculate the residual by inputting this UH into our differential equation, and then we impose the orthogonality with the any vector in the space V. Okay, now you just put R, and we can just take this part to the right side, and we put V. This is for all V. This equation is satisfied for all V's in V. This is one statement. This is I equation. That we are doing the same thing for the last few examples. Now we can take the Cj's out, and we can write this. So we can take this Cj out, and we can write this into this form where Aij's are this and Bi are this. Okay, from this statement we can convert this into set of linear linear equation, and we can solve it to get the values of Cj, similar to the earlier examples. Okay, so let's see the results when we implement this. Okay, so this is result for n is equals to 1. We are using just one basis function. This is sine, which will be something like sine pi x by 2l. So using a function this. Okay, so this function f, I've chosen it to be this sine x1 x square, and length is from 0 to 4, the domain. Okay, so this is the exact solution, this one, and this is the approximate solution. Note that these trial solutions satisfy the essential boundary condition here, but it doesn't matches with the actual solution at this point. Okay, at x equals to 4, the trial and actual solution are not the same. In the previous example, when we specified only Dirichlet boundary conditions, at least the endpoints met for all of the iterations. When we doesn't matter, we take n equals to 1, 2, or 3, any dimension, the trial solution at least satisfy these kind of boundary condition. But here it's not doing so. Why is it so? Because we have not specified the Dirichlet boundary condition at this part of the boundary, which is x equals to 4. Rather, we have specified the Neumann boundary condition. Okay, so Neumann boundary condition was 0. Okay, the derivative was 0 at x equals to 4. So this condition is satisfied, right? So this is the zero line. So you can see that the derivative is 0. So actually our solution is satisfying both the boundary conditions, but you can see them in the different plots, because one is for the derivative and another one is for the state variable itself. Okay, yeah, this is for error and the residue, and the error is quite big because n equals to 1 here. We go on refining, we increase the dimension of our trial space, and this is what we get. Again, you can see that here also the curves don't match, but it is identically 0 and 0 here for the essential and the Neumann boundary condition. We again go for n equals to 5. That's what we get. Again, there is a gap here, although the error is reduced, and Neumann boundary condition is satisfied even for this iteration. That's what we expect. Now for n equals to 10, the first derivative is almost, there is certain gap, but here you can see we have achieved almost 0 error here. Error is pretty low, but the second derivative is still not that accurate, and we'll see that pattern to be carried forward to FEM as well, because you can very easily the solution, like approximate solution for the state variable u will be more accurate as compared to its derivatives. Okay, the error goes on increasing. The solution, the approximation becomes poorer and poorer as you go on calculating the derivatives. Okay, now so let's see very quickly the implementation of this thing in Matlab. We have doing the same thing again and again, so I'll go very quickly through this one. This is a problem that we wanted to solve. Okay, and defining a symbolic variable. The only difference here is now we have this condition, which is Neumann boundary condition now, and again when this is our basis function, and aij and bi are the same, and we define in a similar way, and we again calculate c, we construct our trial solution again, and we calculate our derivatives and the trial solution from this equation. Okay, and we are plotting it here. Yeah, so I'll provide the code, you can play with it. The link will be in the description. If it's not there right now, I'll update it in some time. Okay, so let's go back and continue from where we left off. So what we have now, we know how to implement homogeneous Neumann boundary condition by designing or by intelligently constructing our basis function such that their derivatives become zero at the points at the part of the boundary where the Neumann boundary condition has been satisfied. So it is a bit challenging because the basis function that we have chosen, the sinusoidal basis function, it worked for that, but for different problems the cases would be different, and you need to figure out these basis functions so that the derivatives also become zero and the function itself should become zero at the boundaries. Okay, now what about non-homogeneous boundary condition? Okay, so we solved homogeneous boundary condition. That in itself was very difficult. What about non-homogeneous boundary condition? How can we solve those? For solving non-homogeneous Dirichlet boundary condition, we use boundary functions, correct? So can we use some kind of boundary function for non-homogeneous Neumann boundary condition as well? The answer is yes, we can construct them, but again it will be very difficult to construct that as well. Okay, so can we systematically find out a way? Yes, there is a way, but it is a bit tedious. We'll start from a very simple example and it will extend it to a generic one. So the generic one will be slightly mathematically tedious, nothing much fancy, but just mathematically tedious, and we'll start off with a very simple example. Okay, so here is the example. So we want to solve this problem again. Okay, so previously we selected Fourier basis function that looked something like this. Okay, can we work with normal power series or the polynomial basis? Okay, so we choose these basis function, x to the power I. Now we just choose a dimension to 3 right now, and we calculate the first derivative of the trial solution. Okay, we have constructed trial solution from these basis functions. Now we know that we need to satisfy this condition. Okay, UH dash at L is Q. Now if you evaluate this expression at L, this becomes Q, x becomes L, x square becomes L square. Now from this expression you can separate C. Okay, so C1, we already know what C1 is in terms of obviously Q that we know, and C2 and C3 that we want to find out. So one variable that we wanted to find using solving AC is equals to B is now reduced. Okay, in this case. Now, so will this improve our approximation, or will it degrade the quality of our approximation? I think it will degrade, because the dimension in which you're looking for a solution will now reduce. We'll see. So one coefficient is now dependent on the rest. We have established this. So we put C1 here, we put C1 here. It looks something like this now, and we separate the C2 and C3, the other factors of C2 and C3. So now we have new trial solution. We can write it in this form as gx times d2 phi 2 plus d2 phi 3, where phi 2 are our new basis functions. Okay, and d2 are nothing but C2 and C3. Now this UH is again is a combination of some boundary function and some linear combination of the basis function in some space and the coefficients d2 d3 that we want to find out. Okay, so this gx is now, note that, is dependent on the value of the Neumann boundary condition, okay, here, and x. So we'll see in the next the generic derivation that this x is nothing but some part of your basis function, which is psi 1 here. Okay, this is nothing but psi 1. We'll see those details in the next example. Okay, so let's see the nature of this phi, the new basis function. So phi 2 and phi 3 are these, and we calculate their first derivative. And now note that these basis functions phi are 0, okay, at the point where Neumann boundary essential boundary condition has been specified, and also their derivatives psi 2 dash and psi 3 dash are 0 at x equals to L, where Neumann boundary condition has been satisfied. So by doing these operations, we have achieved what we wanted. We wanted basis functions and their derivative should be 0 at essential and Neumann boundary conditions respectively, wherever they are specified. Now we can write our approximate solution or the trial solution in something like this. Nothing but writing this function in the recognizable form that we have been dealing with. So this is nothing but a boundary function that satisfies both essential and Neumann boundary condition. Okay, this is a Neumann boundary condition, which is just L is equals to Q and G0 is equals to 0. This is some advanced boundary function. Okay, apart from the boundary function that we discussed from in the non-homogeneous Dirichlet boundary condition case, this is Gx. This is more than Bx, and this part is what we want to calculate now. Okay, these are new set of basis functions, and this coefficients Ti is now what we want to find out. Okay, so we can implement a similar thing in Matlab. It is not very complicated. So I mean, once you have this trial solution, the story after this is similar. Okay, so we are not going to see any example of this. So the purpose of explaining this is something different. This will become clear to you at the end of this video. So we are not going to look into example of implementation of this thing, but we'll see a generic expression, a generic form of this discussion. So let's move on to that part. Okay, so let us now derive the generic form, the second order ODE with mixed non-homogeneous boundary condition. Here we'll consider non-homogeneous Dirichlet, non-homogeneous Neumann. In the previous example, the Dirichlet boundary condition was homogeneous. Okay, you can see this. It was homogeneous here. Alright, and this was non-homogeneous. Okay, so let us take these kind of boundary conditions now. Doesn't matter what our problem is, we are just simply constructing our trial solution. Okay, even in the previous example, we didn't use our original ODE. Okay, we are simply constructing our trial solution. The weighted residual statement, and then putting the trial solution in that, and then coming up with the differential the set of linear equations is the later part. But here we are just interested in developing our trial solution, permissible trial solution that satisfy our boundary condition. Okay, the first thing is our approximate solution should be permissible. Okay, so let's see how can we develop this. This is going to be a bit mathematically tedious, but please bear with me. We'll go very briefly through the steps. So this is our trial solution, initial trial solution, which is concerned with only the Dirichlet part. Okay, so this is our boundary function Bx with B0 at D, and psi j is all psi j's are 0 at 0. Okay, this is just if just forget for time being about this Neumann boundary condition. We have just considered how can we satisfy this. Okay, with respect to the Dirichlet boundary condition, this approximation is permissible. Now let us calculate the first derivative of this, and similar to the previous example, we'll separate the C1 and evaluate this expression at L. Okay, we know U dash at L is Q, so UH, which is approximation, should also be Q. So we substitute here Q, and we take out in the next step one coefficient out. Okay, we have taken out from the summation one coefficient, that's why summation is from 2 to n now. Now we can represent C1 in the form as a function of this Q and rest of the CJs. Okay, so this is our C1 is we just taken out C1. So this is this complicated expression is now our C1, similar to the previous example. Now we substitute C1 where? In this part. Okay, for first we separate C1 again in the approximate solution, and we substitute C1 like this. And now the next step, we'll group the summation and the other part out of the summation. Okay, so this is how we get the separated form. So this part is which is out of the summation, and this part is which is inside the summation. This is Cj, you can see here Cj is Ij minus this part divided by C1 psi1 dash at L, okay, multiplied by psi1. Note that this psi1 is a function of x, this also, and these psi1 dash L, psi dash L are the values, okay, of the basis functions, original basis function that we use to satisfy the Dirichlet boundary condition, okay, at L. So these are scalars, okay, this is also a scalar value, and this is a function, this is a function, this is a scalar value, this is a scalar value. Now let us write this into this form. Okay, so here gx is our some superior boundary function, and we have new basis function psi j, which looks something like this yellow part, and we want to calculate this Cj. Okay, so let's see what did we successfully have been able to get a permissible trial solution. Let's check that. For it to be permissible, it should satisfy both the boundary conditions, and also for that the basis function, the psi j, should be 0 at the essential boundary condition, and their derivative should be 0 at the Neumann boundary condition. Are we getting this? Yeah, so let's calculate the first derivative of the psi j, which is something like this. So because only function of x is this psi1 here, so we evaluated it at x equals to L, and this get cancelled out. This is also evaluated at L, so this is also 0. Okay, psi j, this is also at L when we evaluate this expression at L, so everything is 0 now, so this is good. Now psi j at 0, okay, for essential boundary condition, this is, and this is note that psi1 was 0. See, this was already that's what we have been, that's what we started with. So all psi j's are 0, so this is 0, this is 0, so everything is now 0, so this is also satisfied. Now UH dash L should be equal to Q, is it? So for at x goes to L, this expression UH dash L will only consist of g dash x term, because psi j dash are all 0 at x goes to L. This is from this. Okay, so we can write GL as b dash L as b dash L plus this thing. Okay, from here what we get is this is cancel, this is cancel, and what left is Q. So UH dash L is equals to Q. So we have everything now. What about UH at 0? Okay, what about UH at 0? See here, so g of 0, because all psi j's are 0 at x equal to 0, so this term goes out. Only remaining term is g of 0. So g of 0 is here. G of 0 is nothing but b0 plus q minus b dash L, because this is a scalar and side is 0. Okay, so this term finally comes out to be d, because b0 is d and psi1 0 is 0, this is 0, right? So this term goes out, only thing remaining is b0, and b0, what we have already refined, b0 is d. So all the conditions are specified now. So this is what we have, after doing everything, what we have achieved is a permissible trial function. Okay, now why we have been doing this? So we have transformed this initial trial function to a complicated trial function or superior trial function that is satisfy all the boundary conditions. And with that, now we are looking for, since we already know g of x, and we are now looking for a solution for this. Okay, note that gx consists of psi1, okay, one of the basis function of the previous domain, previous space that we were searching in. So what's the problem in this? The problem is it's very for very simple domain it was very tedious. What about complicated domains in 2D and 3D and very complicated coefficients in the differential equation? It becomes very tedious in that case. Okay, now so what we have seen right now, we had to do a lot of stuff to just get to the trial solution, a permissible trial solution, and this makes handling Neumann boundary condition a bit tedious and difficult. It's not impossible, but it becomes very difficult for complicated some kind of they might not be constant values, they could be function of x, the Neumann boundary condition. So in that case it will become a bit tedious and challenging. It can be done, but it's very difficult for complicated domains. So we need something simpler. The another problem here is that it's actually not evident right now, but it's not actually a problem, but it is a constraint, and let's see what it is. So we started with the weighted residual statement for some problem, say example 2, and we used the trial solution, put it in this expression, and what we got is what was this. Note that in this expression, this yellow part is the second derivative of the basis function. What if the basis function that you are choosing, for some reason you can't use the basis function for which the second differentiation of that basis function exists, or they are not differentiable up to second order? What if there is some constraint like that? Okay, then in that case you can't use this statement, because you need to construct such basis function which are differentiable up to second order, but that's what you can't do. We don't know the reason, but suppose you are not able to do. So can we use so what's the solution for this? Okay, so the example of not being able to use differentiable second the basis function that are differentiable up to second order is in FEM. Okay, so in FEM basically the basis functions that we will be using will be only mostly C0 continuous and at most C1 continuous. So C0 means just they have a kink. Okay, C1 is that the derivative will have a kink or something like that. So mostly they will be C0, and they have discontinuous this kind of derivatives, so they are not differentiable up to second order. So in that case, what's the way out? So you might think, suppose someone allows you to use higher order differential higher order basis functions such that the derivatives exist, but this thing sometimes becomes very computationally costlier. This is not evident here in these very simple examples, but for complicated domains handling very complicated geometries, it becomes actually very computationally costly. So what's the way out now? So partially this problem is solved by what is called the weak form. Weak form is nothing but converting your weighted residual statement, okay, into a different form by doing a specific mathematical operation. So what happens by doing that mathematical transformation or mathematical operation? First, Neumann boundary conditions comes out naturally out of that transformation, and you just need to plug in the values. Okay, we'll see how that happens. And second thing is, it reduces the differentiability requirement on your trial solution. Okay, so these two things, that the two problems that we have discussed, there are many problems, but we have just focused on these two problems that weak form solves or help us, or at least partially solves in some cases. So that's what we'll be discussing in the next video. So the whole idea of, or the basic aim of this module was to introduce weak form. Okay, and why the weak form is there, that's why we have been discussing those boundary functions and challenges with satisfying Neumann boundary condition. You will see using weak form we'll be able to satisfy those Neumann boundary conditions very easily, and also the differentiability requirement of your basis function will also reduce. Okay, so those constraints become relaxed, but by doing that we also lose something. What is that? We'll see in the next videos. So that's it for this video. We'll start our discussion on how to get to the weak form, and what do we gain from the weak form, and what all that we can lose from the weak form. Yeah, so that's it for this video. Yeah, thank you.